topic of this presentation is electric turbine. I will briefly introduce it to understand. Main contents of this presentation are: Introduction, Components of turbines, Classification of turbines, Major types of turbines, Applications of turbines, Advantages and disadvantages of turbines, Future trends and challenges of turbines. Now, what is a turbine? A rotary engine actuated by the reaction or impulse or both of a current of fluid, such as water, steam, or air, subject to pressure and usually made with a series of curved vanes on a central rotating spindle. Here are some points to explain it further. A turbine consists of a rotor with blades that spin when the fluid hits them. The rotor is connected to a generator that produces electricity or to a shaft that drives a machine. The fluid can be water, steam, gas, air, or any other substance that flows. Turbines are classified based on the type of fluid, the pressure, the flow, and the speed of the rotor. A turbine works by converting the energy of a moving fluid into mechanical work. Depending on the type of fluid, the pressure, the flow, and the speed of the rotor, different kinds of turbines can be used for different purposes. Here are some examples of how turbines work. A steam turbine uses high-pressure steam from a boiler or a nuclear reactor to spin the rotor blades. The steam expands and cools as it passes through the blades, transferring its energy to the rotor. The rotor then drives a generator to produce electricity. Steam turbines are widely used in power plants and industrial processes. You can learn more about steam turbines from this article. A wind turbine uses the kinetic energy of the wind to spin the rotor blades. The wind pushes the blades, creating lift and drag forces that rotate the rotor. The rotor then drives a generator to produce electricity. Wind turbines are used for renewable energy generation and can be installed on land or offshore. You can learn more about wind turbines from this demonstration. A gas turbine uses a mixture of air and fuel that is ignited in a combustor to spin the rotor blades. The hot gas expands and accelerates as it passes through the blades, transferring its energy to the rotor. The rotor then drives a compressor to draw more air into the combustor, creating a continuous cycle. Gas turbines are used for jet engines, marine propulsion, and power generation. The names of the common components of turbines are: blades, rotor, shaft, generator, nacelle for wind turbines, tower for wind turbines. Blades are one of the most important components of turbines, as they are the parts that interact with the fluid and transfer its energy to the rotor. Blades can have different shapes, sizes, and materials, depending on the type of turbine and the fluid. Some of the common types of blades are: bucket-shaped blades, aerofoil-shaped blades, propeller-shaped blades. A rotor is the rotating part of a turbine that is connected to the blades. It spins as the fluid pushes or pulls the blades and transfers the rotational energy to the shaft or the generator. The rotor can be either horizontal or vertical, depending on the orientation of the turbine. The rotor can also have different numbers of blades, depending on the type of turbine and the fluid. Some examples of different types of rotors are impulse rotor, reaction rotor, propeller rotor. A shaft is a component of a turbine that connects the rotor to the generator or other load. It transfers the rotational energy from the rotor to the electrical or mechanical device. The shaft can be either solid or hollow, depending on the type of turbine and the load. Shafts are usually made by hot rolling and then cold drawn or turned and ground to size. They are typically made of high-strength steel alloys that can withstand high torque and stress. Shafts can also have different lengths and diameters, depending on the size and power of the turbine. Some examples of different types of shafts are low-speed shaft, high-speed shaft, single shaft, multi-shaft. A generator is a component of a turbine that converts the mechanical energy from the shaft into electrical energy. It consists of a coil of wire and a magnet that induce an electric current as they rotate relative to each other. The generator can be either synchronous or asynchronous, depending on the type of turbine and the grid frequency. Generators are usually made of copper, iron, and steel, and are designed to withstand high temperatures, pressures, and vibrations. Generators can also have different sizes and capacities, depending on the power output and efficiency of the turbine. Some examples of different types of generators are steam turbine generator, gas turbine generator, wind turbine generator. Here are some points to explain what a nacelle of a turbine is. A nacelle is a cover that protects the generating components of a turbine, such as the generator, gearbox, drivetrain, and brake assembly. A nacelle is usually mounted on top of the tower and connected to the rotor and hub. A nacelle also contains the control electronics and the yaw system that rotates the nacelle to face the wind direction. Nacelles can vary in size, shape, and weight, depending on the type and power rating of the turbine. For example, a standard 2 MW onshore wind turbine nacelle weighs approximately 72 tons, while a 6 MW offshore wind turbine nacelle weighs about 400 tons. Nacelles are typically made of steel, fiberglass, or composite materials. Nacelles are manufactured using conventional processes, such as casting, welding, bolting, and assembling. Some manufacturers use individual workstations or cells to complete the various stages of assembly, while others use automotive-style moving assembly lines. Nacelles undergo rigorous testing and quality control before they are shipped to the installation site. A tower is a tall structure that supports a wind turbine and its components. There are different types of towers for wind turbines, each with its own advantages and disadvantages. Tubular steel tower, lattice tower, concrete tower. Classification of turbines based on working fluid, pressure, flow, speed. Major types of turbines are steam turbine, gas turbine, wind turbine, water turbine. A steam turbine consists of a boiler, a turbine, a condenser, a feed pump, and various auxiliary devices. The boiler produces high-pressure steam from water and fuel. The turbine expands the steam through fixed and moving blades, which rotate a shaft connected to a generator. The condenser cools down the exhaust steam and condenses it back to water. The feed pump recirculates the water to the boiler for reuse. A gas turbine is a type of engine that uses hot gases from burning fuel to spin a turbine and produce power. The gas turbine works on the principle of the Brayton cycle, which involves 4 steps: compression, combustion, expansion, and exhaust. The gas turbine can be used for various applications, such as powering aircraft, trains, ships, generators, pumps, and tanks. A wind turbine is a device that converts the kinetic energy of wind into electrical energy. A wind turbine turns wind energy into electricity using the aerodynamic force from the rotor blades, which work like an airplane wing or helicopter rotor blade. When wind flows across the blade, the air pressure on one side of the blade decreases. This creates a lift force that makes the blade rotate. The rotation of the blade drives a generator that produces electricity. A water turbine is a device that converts the kinetic and potential energy of water into mechanical work or electricity. Water turbines are mainly used for generating electric power from water sources, such as dams, rivers, or oceans. Water turbines have different types and designs, depending on the water flow and head. Some common types of water turbines are Pelton turbine, Francis turbine, Kaplan turbine. Applications of turbines include electrical generation, engines, propulsion systems, aviation, electrical power generation, oil and gas industry, marine propulsion, turbo generators, turbo compressor, automotive sector. Here are some of the advantages of turbines in general. Turbines are clean and renewable sources of energy. They do not produce harmful emissions or waste that pollute the air, water, or land. They use natural resources that are abundant and inexhaustible, such as wind, water, and gas. Turbines are cost-effective and efficient. They have low operating and maintenance costs compared to other power sources. They can also generate high amounts of power with relatively small sizes and weights. Turbines are flexible and adaptable. They can work in different settings and conditions, such as rural or remote areas, farms and ranches, coastal and island communities, and industrial plants. They can also be integrated with other energy sources and systems to optimize performance and reliability. Here are some of the general disadvantages of turbines. Turbines can cause noise and visual pollution. Wind turbines can be noisy when operating, as a result of both the mechanical operation and the wind vortex that's created when the blades are rotating. Some people also find wind turbines unappealing aesthetically, especially when they are built in large numbers on scenic landscapes. Gas turbines and jet turbines can also produce loud noises that can disturb nearby residents or wildlife. Turbines can have some adverse environmental impacts. Although turbines do not produce harmful emissions or waste during their operation, they can still affect the physical environment around them. For example, wind turbines can pose a threat to some wildlife, especially bats and birds, who may get injured or killed by the spinning blades. Hydroturbines can alter the natural flow of water, affecting the aquatic ecosystems and the availability of water for other uses. Gas turbines and jet turbines can also contribute to greenhouse gas emissions when they use fossil fuels as their source of energy. Turbines are intermittent and unreliable. Turbines depend on the availability and consistency of the fluid that drives them, such as wind, water, or gas. However, these natural resources are not always predictable or stable, and they can vary depending on the weather, season, or location. This means that turbines cannot generate electricity or power continuously or on demand, and they may require backup systems or storage devices to ensure reliability. Turbines are expensive and complex. Turbines require high initial costs for their installation and construction, especially for large-scale projects that involve multiple units and extensive infrastructure. Turbines also require regular maintenance and inspection to ensure their optimal performance and safety. Turbines may also face technical challenges or failures due to mechanical wear and tear, corrosion, erosion, or damage from external factors such as storms or lightning. Some general aspects that can be considered for improving turbine technology are: increasing efficiency and output. This means making the turbines produce more power with less fuel or fluid input, reducing the losses and waste of energy. Some methods for achieving this include using larger or more aerodynamic rotors, optimizing the design and materials of the turbine components, improving the cooling and lubrication systems, enhancing the control and monitoring systems, and integrating the turbines with other energy sources or storage devices. Reducing cost and complexity. This means making the turbines more affordable and easier to install, operate, and maintain. Some methods for achieving this include using standardized or modular designs, simplifying the turbine structures and systems, increasing the durability and reliability of the turbine components, applying preventive and predictive maintenance strategies, and reducing the environmental and social impacts of the turbines. Adapting to changing conditions. This means making the turbines more flexible and responsive to the variations in the fluid input, the power demand, and the external factors. Some methods for achieving this include using variable speed or variable geometry turbines, implementing smart grid or microgrid technologies, enhancing the security and resilience of the turbines against threats or failures, and developing new or alternative fuels or fluids for the turbines. Depending on the application and the environment, some of the future trends and challenges of turbines are: wind turbines. Wind turbines are one of the most widely used and promising sources of renewable energy. However, they also face some technical and environmental challenges, such as increasing the efficiency and output of the rotors, reducing the cost and complexity of the installation and maintenance, adapting to the changing wind conditions and power demand, and minimizing the noise and visual pollution and the impact on wildlife. Gas turbines. Gas turbines are commonly used for power generation and propulsion in various industries. They have high power density and reliability, but they also have some drawbacks, such as high fuel consumption and greenhouse gas emissions, low efficiency at part load, high noise and vibration levels, and complex cooling and lubrication systems. Some of the future trends and challenges of gas turbines are improving the performance and durability of the turbine components, developing new or alternative fuels or fluids, enhancing the control and monitoring systems, and integrating with other energy sources or storage devices. Hydroturbines. Hydroturbines are another important source of renewable energy that use water flow to generate electricity. They have low operating and maintenance costs, but they also have some environmental and social impacts, such as altering the natural flow of water, affecting the aquatic ecosystems, displacing local communities, and posing safety risks. Some of the future trends and challenges of hydroturbines are optimizing the design and operation of the turbine systems, reducing the environmental footprint and mitigating the negative effects on water resources, enhancing the security and resilience of the dams and power plants, and expanding the potential sites for hydropower generation. Steam turbines. Steam turbines are widely used for power generation in thermal power plants that use coal, nuclear, or biomass as fuel. They have high efficiency and reliability, but they also have some limitations, such as high capital cost, long startup time, high water consumption, and high emissions of pollutants. Some of the future trends and challenges of steam turbines are increasing the temperature and pressure of the steam cycle, improving the materials and coatings of the turbine blades, reducing the water usage and waste heat generation, and integrating with carbon capture and storage technologies. Jet turbines. Jet turbines are mainly used for propulsion in aircrafts and rockets. They have high thrust-to-weight ratio and speed, but they also have some disadvantages, such as high fuel consumption and noise levels, low efficiency at low speed or altitude, high operating temperature and stress. Some of the future trends and challenges of jet turbines are developing more aerodynamic and lightweight designs, using more advanced materials and cooling systems, enhancing the combustion efficiency and stability, reducing the noise and emissions. Thanks for watching. That's all for today's video on electric turbines. I hope you found it useful and interesting. For detailed study of each type of these turbines, keep watching my next videos. I welcome your suggestions in comment box on what topic you want me to cover. If you want to see more videos like this, please subscribe my channel and click the bell icon to get notified whenever I upload a new video. Never forget to like and share.